Right, so hi everyone. Thank you very much to the organizers for allowing me to give this talk. It's really a privilege. So today I want to tell you about our work on extending these fuzzy sphere models to fractional filling, or in other words, using anyons to regularize 3D CFTs on the fuzzy sphere. So this is based on work that you can find on this archive preprint that's soon to appear in PRX and is done in collaboration with a number of great people who are involved in this conference as well. So Rui Hua, who is now at Berkeley, Nicolas Regnault, who is at Flatiron, and Zlatko, who is my supervisor at Leeds. So let me dive right in and tell you about the motivation. So the idea is that most fuzzy sphere models that have been proposed so far work at an effective kind of integer number of Landau levels being filled. And there are many examples, but I just want to focus on this 3D Ising model because we'll come back to it later. So this has n electrons in n orbitals. So effectively one Landau level filled, and then you add this spin degree of freedom. So people also say that it's at 1/2, but it's effectively one Landau level filled. And this is very important, even though it's not mentioned too much, because it ensures that all the charge excitations of the fuzzy sphere are gapped. And so this makes the charge sector of this fuzzy sphere inert, which allows us to observe all this nice CFT data in the charge neutral sector. So the question that we want to ask is, can this method work at systems without integer filling? And to do this, we will go to a series of fractional fillings where we know that we have a many-body charge gap opening. So of course, here I'm talking about the fractional quantum Hall effect, which some of you are familiar with. So basically, this comes with some exotic charge excitations, which usually have fractional charge and fractional exchange statistics. So there are both advantages and disadvantages to working with such models. So for one, we can now test whether the fuzzy sphere method works by starting from either bosons or fermions as our microscopic particles. So it's very easy to construct fractional quantum Hall states from bosons. So this is one way to explore this. Another thing is that at fractional fillings, we do not have the microscopic parity that corresponds to space-time symmetry. So if indeed you realize a CFT that has such a parity symmetry, then this will become emergent. So we can study this as well. In terms of disadvantages, there are some obvious things, such as, now we have a problem that's a bit computationally, that's a bit more difficult. The Hilbert space dimension increases faster at fractional filling, so we'll have access to fewer finite size systems. But more importantly, we now have additional intra-Landau level charge neutral excitations that were not present at integer filling. So this is kind of a very basic plot in FQH where I'm showing this magnetoroton branch. This is a gapped kind of charge neutral excitation that corresponds to density wave-like excitations on top of this ground state here. And these will appear exactly in the same sector of the Hilbert space as all the CFT data that we're after. So we need to understand how to separate such states, even though they're gapped, from the universal states that come from state operator correspondence. So let me tell you.
A lack of the exact parity symmetry, also a disadvantage? If you have a CFT that has parity symmetry, isn't that better?
I guess it depends how you interpret it. I thought it would be interesting to study it as being emergent and maybe see if there is some kind of operator that sort of corresponds to it and which becomes, which has a physical value in the thermodynamic limit or something like that. But yeah, I guess you can view it either way. Okay, so let me tell you about the model. So again, we'll focus on this beautiful model for the 3D Ising, which works at nu = 1. And so the interaction is this one where we encode the Ising interaction in what we call this interlayer interaction, because it only couples spins or flavors which are opposite, so n up and down. And then we have this transverse field as well. So what we want to do is study the same 3D Ising theory, but on top of a fractional quantum Hall state. So in the main talk, I will focus on filling 1/3, and we will add this intralayer interaction, which is very similar, but now couples spins which are alike. So just to reiterate in terms of symmetries, we preserve the Ising Z2, but we are not particle Hall symmetric anymore, and so the space-time symmetry is not there in the EV. So in terms of the phase diagram, we expect something like this. Because we would like to have a decoupling between the charge and the spin sector, we expect to see FQH type physics throughout the phase transition. So we expect to see these gapped modes both in the ferromagnet and in the paramagnet states. And then at the critical point, we expect to have this gapless tower of states that corresponds to the CFT. In terms of the model, the intuition for constructing these models starts from the so-called parent Hamiltonian construction of fractional quantum Hall states. So these are Hamiltonians which stabilize any given or most given FQH states as a zero mode. And so in the case of the Laughlin state, which is written here, so Laughlin first wrote this variational wave function. This is the zero mode of a Hamiltonian that only has V0 and V1. So this is a single layer Hamiltonian. And so starting from this, we can come up with a minimal model that has both intra and interlayer pseudopotentials. And so the first two pseudopotentials are taken from the from the parent Hamiltonian, V0 and V1, and we set them to 1. So we don't need to tune these. And then to add the Ising interaction, we add two additional pseudopotentials in the interlayer term. So here these values are already fine-tuned so that we observe the best critical spectrum. Okay, so let me tell you a bit about the critical point and the critical spectrum. So we have two methods of identifying the critical point. The first one is a bit more physical. So because we expect to have this persistent FQH physics, we use this mean field theory, which discards correlations in the spin sector and preserves correlations in the charge sector. So we work with this family of Laughlin states, which have this variational parameter theta, so all the spins point along this direction theta. And you can get them numerically by diagonalizing this projected interaction along the direction theta. So what we're interested in is the optimal such state that describes the ground state wave function at a given h. So we just optimize the overlap with this Z2 even superposition. So you see that this works quite well. We start from the ferromagnet at theta equals 0. And then this gradually tilts to pi by 2, which is the direction of the transverse field. In terms of overlap, we see that this is quite high, but there is a kind of characteristic dip at around 0.13 that signals that here the spin correlations are significant, and so we should expect a phase transition.
Sorry?
Yeah.
What filling are you at?
So we're at Landau level filling 1/3 or total filling 1/6 if you consider the flavor degree of freedom. Okay, so of course this is not very exact. You can use the same kind of CFT order parameter finite size scaling. So in the case of this model, we will stick to the layer magnetization, this m squared. So if you do the same collapse, you will find that the curves. You will find that the curves collapse around the same point, 0.13. So this is how we identify the critical point. Let me show you the spectrum at the critical point. So here I again make a comparison between the data of the microscopic model, the circles, and then the thick lines are levels from Bootstrap. So you see a decent state operator correspondence at low energies and low angular momenta. There are significant finite size effects, but at least for most states there is a one-to-one correspondence between the states of the Ising CFT and the states of this model. And keep in mind that this is a much smaller model at n equals 8 particles. And what I want to point out are these states highlighted in green here. So this branch here, and then this branch here. So they look a lot like the magnetoroton branch that I've shown before. And we identify them as such by using the mean field theory again. So we use the single mode approximation, which is a way of approximately constructing these states using a density mode. So here the mean field is this optimal state that we've already found. So we don't need to do any optimization. We just construct these states. And then the green color on those plots is the overlap of any given eigenstate in a particular L sector with this mean field state. So you see that only one state has most of the overlap with this magnetoroton, which says that most of the weight of this gapped state is captured in that eigenstate, and there is very little mixing with any universal state, even though they might be at very similar energies to the CFT states. And just to convince you even further, we can choose, for example, this sector, and I'm showing the energy levels as a function of system size. So you can see that the green states, they are tracked by overlap, and they seem to converge to some finite value of the energy, passing through all of these gapless states. So, okay, so this is kind of the evidence that we have for the 3D Ising transition just by looking at the spectrum and optimizing this, but can we quantify deviations? So I won't talk too much about the theory behind this because there have been some great talks in the previous sessions. So we use conformal perturbation theory, where you can write an effective Hamiltonian near the critical point by just adding these perturbations. And the energy corrections can be written just in terms of, just by using the properties of the CFT. So we keep it quite simple. We pick 4 energy levels, so 2z even, 2z odd states, and we add 1 relevant and 1 irrelevant perturbation. So here the continuous lines are the raw data of the model. The dashed lines are the fixed energy levels. And then these now are very, very close to the conformal bootstrap levels, which are these very thin lines. So we see that this works for a wide range of h. In terms of the perturbation couplings, we see that they have the expected scalings. So the relevant operator changes sign at the phase transition. So there is an obvious drift, but there is still important information here. This point where this changes sign is the point where you should see the best spectrum at a certain finite size. So this is what I was showing you before at n equals 8. This is where this is taken. And then for g epsilon prime, this obviously, this coupling gets smaller with system size. So I want to point out 2 things before I move on from this. The first one is that we see this approximate collapse in the curves of g epsilon, which doesn't happen where this is equal to 0. And if you remember this value, this happens at a value that's very close to where we saw kind of a crossing in the order parameter lines. And of course, these things are related. That's because you can use conformal perturbation theory to see the mixing between the eigenstates, which then creates a correction in the order parameter. So this is going to be dominated by the epsilon coupling. And because there is an approximate collapse here, we will see an approximate collapse. So these things are obviously related. Now, in terms of the drift, so we're not quite sure where this comes from, even though this is kind of a generic feature that seems to show up in most models except this 3D Ising model at integer filling. But what we can look at for sure is whether this is affected by the state in the charge sector. So whether the FQH has any effect on this. And so to do this, we march on with this perturbation theory. And we will consider a coupling between the CFT and the charge sector using some combination of operators, for example, an epsilon and a density mode that creates a roton. If you project this back into the CFT subspace, you will get a perturbation at second order, which depends on this 2-point correlation function of the density fluctuation. So this is a very well-known quantity in FQH. And because this is a gapped mode, so at long distances, this will decay exponentially. So we don't need to worry about long distances. At short distances, this is dominated by some correlation hole with some algebraic form that we know. Since we're focusing on short distances, these CFT operators, we can use the OPE to write down the new terms that are being generated. And so what this is saying is that this coupling between the CFT and the roton creates additional CFT terms in this CFT subspace. And we can write the additional coupling that's being generated after approximating this integral. And of course, it will be inversely proportional with this roton gap. So, this could in principle affect the drift that we're seeing.
So what's the row here?
This row?
Yeah.
This is the density in the ground state, the electronic density. And it comes from this term, from here. This is row 0, but it's actually row 1/3. Okay, so to test this in our microscopic model, we can do a very simple thing. We can just vary the V1 intra pseudopotential because this is not really coupled to the phase transition. So we can vary this without changing this critical point too much. And the Roton gap is directly related to this value. And so if we do CPT at a range of V1 intra values, we see that indeed there is a small change in the G epsilon. And if you look at how it scales with the V1 intra, it scales, it's inversely proportional to the magneto-Roton gap. So this is all correct. But we also notice that the curves of the same color, so at the same value of V1 intra, at different system sizes are still systematically spaced apart. So this doesn't really explain any of the systematic drift that we're seeing in this model, which is kind of reasonable because, again, this is a generic feature in a lot of fuzzy sphere models, not just this one at fractional charge, at fractional filling. Okay, so let me get to my last content slide. So far I focused on filling 1/3, but there's a lot more fractional fillings which host FQH states. So let me for now just focus on this hierarchy, first constructed by Laughlin, which is at filling 1/Q. So these states are all quite similar with each other. They have a billion anyons of charge E/Q. They have kind of similar neutral modes to the state that we've seen so far, but they can be both bosonic or fermionic depending on the parity of this of the filling factor, as you can see from this wave function here. And to construct models at such a filling, we follow a very similar prescription. So the first number of pseudopotentials is just taken from the parent Hamiltonian of this state. So the first Q-1 pseudopotentials, we don't need to optimize. Then what we do to get the Ising transition, we add 2 more Ising interlayer pseudopotentials where we believe this Ising interaction is encoded. So effectively, for any value of Q, we have 3 tuning parameters. So we have VQ-1, VQ, and H. So if you're at any fractional filling, you will have 3, whereas before, I guess at integer filling, you only had 2 because you could set one of these to 1 and then not have to worry about it. So the spectra look something like this. Indeed, this works for both 1/2 and 1/5. So the 1/2 state is bosonic, and the 1/5 is fermionic again. We see the state operator correspondence at low energies. We see the same magneto-Roton branch that's identified with mean field. And one more thing that I want to point out is that the optimized kind of Ising pseudopotentials hover around the same value. So we don't really have a quantitative understanding of this, but it seems to be implying that the Ising interaction is genuinely only living in this space and not in the first part of the Hamiltonian. So let me summarize what I've told you in this talk. We have extended this fuzzy sphere method, at least for the 3D Ising, to models like fractional filling. We have identified a way of understanding these charge neutral excitations and kind of disentangling them from the universal information of the CFT by using this mean field theory. And we can understand, of course, finite size effects using conformal perturbation theory. In terms of open questions, there's a few interesting things. Of course, we have this decoupling, this very strong decoupling between the charge and the spin sector that's already there, even at small system sizes. So this is one thing that's worth looking into more. There is this systematic drift in the critical point that doesn't seem to be related to our charge state, but is something more generic. And maybe the last point that I find to be most interesting is that understanding these models at fractional filling allows us to look at more interesting transitions. So for example, we can consider transitions between bilayer FQH states that live at the same filling but have intrinsically different topological order. So for example, there is one transition between the Pfaffian state, which is a state with non-abelian order, to this Halperin 220 state. And this is predicted to be continuous and to be the free Majorana fermion. So this hasn't been realized on the fuzzy sphere yet. And it's a very interesting thing to think about. And there's also, if you want, more kind of exotic phase transitions, such as this XY star between a fractional quantum spin Hall insulator and a superfluid. So yeah, thank you very much for your time, and any questions?
Questions? Yeah.
Just curious, do you know how to do things other than 1/2 locking, for example?
Yeah.
Is it possible to do
We had
2/3 or?
So the only thing that we had to look at was nu=1 Moore-Reed bosons. I didn't show data for it. It kind of worked, but the state operator correspondence kind of degrades quite fast. Yeah, I mean, we claim that it works, but we don't have that much evidence for it. And the model that you construct is very similar. You have to add this parent Hamiltonian, which is a V0 in the case of bosons at nu=1, and then add 2 more interactions. But this is only for Ising. Yeah. And I guess a particle hole kind of conjugate state like 2/3 is probably not too far from what we prescribed here. I'm not sure. Yeah.
So in our paper with Loic and Andreas, we have a proposal which could explain these drifts. I don't know if you saw it.
Yeah, the torus, right? Or as in the curvature that is not present if you look on a non-curved.
Yeah, so the proposal would be that it's a coupling to curvature, and then this has a consequence. First of all, that the drift has to go like 1/n up to the coefficient, and then it could be tested by going to a torus where there should be no drift. The 1 + 1 there's no drift.
Yeah, we haven't looked into this like quantitatively just to fit this.
Yeah, it's 1/n or not.
Yeah, it's definitely worth looking into. But yeah, there is this study on the 1 + 1 fuzzy circle, right? And I think they still see a bit of drift in the coupling. So maybe that's one thing to be looked at carefully.
1 + 1 fuzzy.
Yeah, there is a study on.
How can it be fuzzy?
It's the fuzzy thin torus. It's
fuzzy torus.
fuzzy torus, yeah. So yeah, I'm not sure. It's an interesting idea. We'll have a look at it.
Yeah.
Does the CFT spectrum also appear in non-neutral sectors?
Sorry, what appears in non-neutral spectrum?
Does the CFT spectrum appear?
Oh, right. I don't have a definitive answer for that. We've looked into it. So one thing that you can think about is adding a charge flux, a flux quantum to your model. And I guess that would create a skyrmion in this case. And we have had a look at the spectrum, but we don't understand it fully. The one thing there is that the skyrmion has, so the ground state in that case has a non-zero angular momentum. So you start from something like n/2. And there is some remnant of the CFT tower of states, but there is other stuff that we don't really know. Yeah.
Yeah.
So it's a bit of a naive and orthogonal question, but have you investigated in a regime where you pick up some of the fractionalization of the charge for your spin properties? Because here you're completely decoupled.
Yeah. Yeah, I mean, we were after a model where these are still gapped, because otherwise we're not sure what to expect. And so if you want to actually have them affect the properties of the CFT, you probably have to close that gap. So no, we haven't had a look at that.
Yeah, what exactly would be not exact decoupling? Because if you have an Ising CFT, it has to be decoupled from.
Yeah, I guess that is just by definition. Yeah, no, that's a good point. We don't know what the spectrum would correspond to if they are strongly coupled.
That would be different.
Actually, follow that discussion. So, what about your study composite fermion and then try to have an Ising transition on top of it? Then it's some non-thermal liquid, right? This Ising pneumatic. Oh, so it has a 1 gauge field, so then it's more embodied.
So you mean if you soften the roton to close the gap there?
I'm just saying you have a composite from a liquid.
Right, conformable from a liquid, yeah.
Coupled with Ising CFT.
Well, but Yinchen, you can do something simpler. Where you can, if you tune to the nematic critical point, then the magnetoroton will basically become gapless as well.
Which is just a nematic. Yeah, I mean, I'm not sure what one would expect there if you couple this with the Fermi surface, but we also haven't looked at that. Yeah, this method is kind of a general prescription, at least when you know what kind of gapped modes you have. We would have to think a bit more if we go to the CFL.
Maybe the puzzle is that, okay, it's this magnetoroton. Okay, it's gapped, okay, but some states which are as heavy as the magnetoroton or even slightly heavier are still have a good agreement for those states. So somehow it decouples from the Ising CFT at a scale which is higher than its mass. This magnetoroton, which is surprising.
So sorry, so which states, if not the magnetoroton? Or
No,
just
I thought that from your plots it seemed to be the case. Okay, the magnetoroton was of course junk from the CFT point of view.
Yeah.
But there were some states which are as heavy as magnetoroton, which you still said it was CFT states.
Oh, I see. Well,
So that's what I'm saying. It looks like this magnetoroton decoupled from the CFT at some scale which is higher than its mass.
yeah, I'm not making a claim about the rest of the many of the other white states here. I mean, these are still small system sizes, and obviously what you're seeing here is junk as well, because this branch is tailing. This is like 6 particles, right? You cannot expect, and probably many of the states here in this dense part will disappear just because we will increase system size. So I'm not sure. This approach only works for the roton, not for.
Thank you.
So far we don't understand anything about the other junks.
Yeah, we haven't looked at it exactly. I guess if there's any mode that you know exactly how to construct for the Laughlin state, you can try to identify it here with a very similar approach. So that's what this model offers.
Have you compared to the spectrum without spin?
It's compared what exactly?
So just remove the spin degree completely.
Yeah, so I mean,
The spectrum.
in some sense, that's exactly what we do. So we take the states of the model without spin, which is this projected model. Oh, this is the single layer model. It's the bilayer interaction projected along one direction. So this is like, and this has. This is not the exact parent Hamiltonian of Laughlin, but is some state in that class. And we take those states, which have some effective orientation, and we embed them in a bilayer model, and then we take overlaps. So basically, we have some sort of one-to-one correspondence. But we only focused on the roton branch. There's obviously a lot of other states that you can try to make a correspondence. So yeah.
Yes. Can I just add that we know what the other states are? They are composite fermion excitons. So composite fermion theory has figured them out. Yeah.
But this is the lowest lying one. So, you know, if you go higher in energy, the CFT states are not well defined there anyway. So at this point, it might not be meaningful to make that comparison. Andreas, yeah. Sorry.
Yeah, my question is about the scaling of this. So the magnetoroton is really a physically gapped excitation, which means that there's a gap scale which is independent of system size for large enough number of electrons.
Yes.
But the CFT spectrum still collapses as 1 over R.
Yes.
So do you see a clear trend in the numerics that basically in the scaling, like in a set of units where you plot the CFT spectrum, the magnetoroton should actually move up with system size? Is there a clear trend?
So this is the trend. It's not rescaled exactly as you're saying. It's just the raw gaps. But these are CFT states which go gapless. I'm not plotting the whole range because it's a bit of an empty space.
So this Q relates to system size?
This is system size.
Okay.
So these states are gapless, whereas if you track the roton states by overlap, you see that they go up. Maybe the green is not very obvious here, but these are the green states and they go up. They pass through these CFT states unaffected.
Okay, that's nice.
All right. Well, thank Cristian again, and.